We're going to be talking about equilibrium as well as the equilibrium constant K in this PowerPoint. Plainly put, equilibrium is the condition that most chemical reactions assume when the forward and reverse reaction rates are equal. Take the example of water in a plastic bottle in a state of equilibrium. The water is evaporating and the vapor is condensing. You don't see the water levels changing because the reaction rates are equal. There's a constant, more obscurely called the law of mass action, which is really the equilibrium constant K. The law of mass action, or more simply the equilibrium expression for a given reaction, is this. Where C and D are the products and A and B are the reactants. The exponents represent the coefficients in the balanced equation and the brackets indicate concentrations in moles per liter. So, we know that C and D are the products, so what do you think a K greater than 1 says about the state of the system at equilibrium, or less than 1? So if the K value is less than 1, the reactants are favored, and if the K value is greater than 1, the products are favored. And if it's equal to 1, neither are especially favored. Oops, going back. Okay. So if we have a system containing hydrofluoric acid, which is a weak acid, and all that means is that this system will have equilibrium going on. So the concentrations at equilibrium are observed to be 2 molar for the acid, 1 molar for the hydrogen ion, and 1 molar for the fluoride ion. So these ions are the products. So therefore we have that equation and we have the now all we need to do is to substitute the values into the equilibrium expression. So we have 1 times 1 over 2, which equals 0.5 for the K value. So this example was one I just made up, but it reflects the reality that in a state of equilibrium, this acid actually has less product than reactant in its system. So this can be seen algebraically, since the reactants, the denominator, are larger than the product if the K value is less than 1. So lastly, we'll end with fun. Types of K values or constants. They're all the same thing, it's just that they're named according to the situation. For example, Kc is just the K constant when we're dealing with concentrations in moles per liter. Kp is used for a situation where we're using pressures. So just to re-emphasize, that means that in K expressions we can also use pressures in addition to concentrations. In atmospheres, of course. Ka refers to a system where a weak acid is dissociating, for example, hydrofluoric acid, which we did previously. Kb is used for weak base dissociation, which is the same concept. Kw refers to the system when water is being ionized. And Ksp refers to the solubility product. So what that is referring to is simply when you have an ionic solid dissolving. And you can think of it like not all solids entirely dissociate, and that's where you have the equilibrium going on. So those are the types of K constants, and that's a quick overview of what equilibrium is.
Okay, so today I'm going to be teaching you about solubility equilibrium. In solubility equilibrium, there are 2 basic things you need to know. The first thing is the Ksp. The Ksp is the solubility constant, which tells you how soluble the solid or whatever you're calculating is. The solubility constant could be calculated using the concentrations of the products, which is expressed in brackets. The units of this is molarity, which is moles of solvent per liters of solute. First, let's do an example problem. When you see an example problem like this, the first thing you need to do when setting up is to write an equation, as I have done here. This equation will tell you the elements and compounds that you need to calculate, and then to get the Ksp, which is what they're asking for. Since they gave us the amount in grams, we will first need to convert the grams into moles. So let's write this out. This is 3. Once you write this out, you have to find the molar mass of the PB3ASO42, which turns out to be 899.48 grams per mole. By dividing the grams per liter by the molar mass of the molecule, you will get that the molarity is 0.027 moles per liter. Once you have the molarity of this, you could use an equation to calculate the concentration of the products of this equation. Since there are 3 molecules of the PB for every one of the PB3ASO42, you'll need to multiply the concentration of this by 3, which will give you 0.01881 for the molarity. For the ASO4, from the equation you will see that there are 2 molecules of this for every one of the PB3ASO42, which means you will need to multiply its concentration by 2, which will give you 0.054 molarity. Taking these 2 molarity numbers, you could calculate the KSP, which is the product of the concentrations of the 2 molecules. KSP is PB2 plus times ASO4 3 minus. Since there are 3 molecules of PB2 plus, for every 1 molecule of PB3ASO42, you need to write a 3 as exponent here, and a 2 since there are 2 ASO4s. By taking the concentrations of these 2, which is 0.081, and multiplying them together, this one's 0.054, you will get that the KSP of this would be 1.55 times 10 to the negative 6.
Now we are going to learn about the common ion effect. This can be demonstrated with a sample problem. What amount of AgCl will dissolve in a 1 liter solution of 0.1 molarity NaCl with a KSP of 1.6 times 10 to the negative 9 molarity? First, you should write the equation. In this case, silver chloride is being dissolved, so it will dissociate into silver ions and chloride ions. Then set up an ice table. An ice table is basically where you organize the problem, so it shows the initial concentration, the change in concentrations, and the concentration after the system has reached equilibrium. In this case, you put X for AgCl because it's an unknown concentration, 0 because there's been no products yet, and 0.1 because there's already 0.1 molarity Cl minus from the NaCl. And then you write the change, which is minus X, and plus X. And then write the equilibrium, which is 0, X, and 0.1 plus X. Now we are going to solve for KSP. The KSP of silver chloride is 1.6 times 10 to the negative 9. And you can set that equal to Ag plus and Cl minus because that is what AgCl dissociates to. And if you remember the values from the ice table, you can substitute X for AgCl and 0.1 plus X for Cl minus. However, X is a really small number, so you can just assume that X is negligible. And so you end up with 1.6 times 10 to the negative 9 equals negative 1 X. And when you solve for X, you'll end up with 1.6 times 10 to the negative 8. Now you have to convert to grams per liter. So you'll have to multiply that by the molar mass, which is 143.323 grams per 1 mole. And you will end up with 2.29 times 10 to the negative 6 grams per liter. And so that's your answer. 2.29 times 10 to the negative 6 grams of AgCl will dissolve.